So I kind of wanted to make a quick video talking about the state of large language models in the world of computer science as well as programming, because I think in a lot of ways I don't want to say misinformation about it, but there's definitely a lot of confusion, concern, scare going on in the world of computer science, and how is things such as large language models going to change programming. There's a lot of news about people like Dario Amodei constantly going around saying software engineering positions, especially like the entry-level software engineering positions, those are going to be gone in the next 6 to 9 months, but he's also been saying that for the last 24 months. And I think there's a lot of misconceptions about large language models, as well as how useful they actually are when it comes to programming, especially in the realm of, can they actually realistically achieve this, artificial general intelligence, or they can achieve this, ability to one-shot code in the first place, and as well as also just kind of give some comments and reflections on kind of how I feel universities could be teaching computer science better in this world of artificial intelligence. But I kind of wanted to start my talk, or start this video talking um, actually with a quote from the Primogen, who's a software engineer. He used to work at Netflix. He's a very popular YouTuber now in the world of computer science and programming. And he recently gave a presentation at the Omicron conference, which was run by 37 Signals and DHH. And he said that large language models and AI systems, or what we refer to as AI now, all it's doing is it's lowering the cost of a single line of code while also causing the price of a single good line of code to skyrocket. And that comment really stuck with me. Not necessarily in the because what I really extrapolated from that was the landscape is shifting from more less of an ability to actively apply what we learn in computer science and CS coding, like the ability to apply the code, to really prioritizing a much stronger understanding of the knowledge and the theory behind it. Because if you learn the theory, you can easily apply the skill. If you learn the theory, you could just look it up with different programming languages and apply it. You know, if one understands how I don't know, like how Dijkstra's algorithm works, one could implement Dijkstra's algorithm in C++, in Java, in Rust, in Go, and Python if you're a psychopath. But if someone is able to just write code without really understanding the theory and the algorithms behind it, those I think are the people who are really going to be affected by AI and large language models. This inability to learn and create is really where it's going to be. The thinking outside the box is really what's going to get rewarded, in my opinion, in this new generation of computer science and programming, which kind of ties into my feelings about universities as a whole. I don't know if this is, a symptom of universities in other parts of the world, but I do know that from my personal experience, I attended the University of New Hampshire. I feel the mentality that we have where we really prioritize application of computer science. So application as in like programming and being able to actually, implement an algorithm. Not necessarily that it's a bad thing, but I definitely have very mixed feelings about that overall. Because I feel like in this new generation of computer science, being able to know how to program an algorithm in Java or Kotlin or C, that's a skill that's actively going to be going downhill relatively quickly. It's really going to be a lot more, can you look at code, can you parse and understand what the code is trying to do, and then can you identify bugs with it. So not necessarily that like computer science and programming, or like an ability to program as a skill, is going to go away completely, but understanding the theory is going to be a much higher skill, especially as these large language models get better. What's really going to become important is being able to come up with an idea or see a problem, being able to visualize the theory that we can use to apply to these, apply to solve the problem, and then actually use the large language model to not only help us implement the code, but then we also still have the skill set to go back and look at the code that the large language model has written, something such as a DeepSeek or a Claude Code or Codex, and look back at that code and see how that code has actually been implemented. And I actually have a relatively good example right here. This is actually one of the projects I've been working on for one of my classes. It's a very simple I call it a transpiler. It's really a translator, and all it does is it asks you input like a string of MATLAB code that you have. So like for example, sine x times cosine pi. This is a really conventional MATLAB string, and what it does is it converts it to the equivalent in Julia. It's a really simple project, but I wanted to showcase the actual code here, and from this you can see, I have libraries, special character, special character dictionaries, and then you'll notice a lot of this, and then you'll notice quite a bit of the code here is actually generated using a large language model. In particular, I'm using a coding agent called Pi, specifically, primarily with the Kimi K2.6 coding model. But this wasn't a one shot. This wasn't like my prompt for these large language models wasn't something like, write me a program that will translate, a line of MATLAB code into Julia code. You can't be that vague with large language models. You still have to understand how you want it implemented. So I actually spent several days actually working on this. And actually, if I were to go over to my Obsidian, you can actually see the notes that I was writing about how I want it to work. Have an index of knowledge about the syntax of Java. We're going to sort MATLAB functions into a key value system, with the key being the function and the value being the Julia equivalent. If it's a number, it should be able to place the function into a stack so we can reassemble the function as such, which means that we can handle nested functions such as, sine of cosine of something if we want to do something crazy like that. I wanted to suggest the best value type for variables in Julia, because Julia can differentiate between an integer and a float, whereas MATLAB can't. But there's also, how did I want the breakdown of it to work? How did I want it to be able to break apart, a complicated string like, sine plus cosine to the fifth power, whatever I wanted it to do? How did I want to break that down? So I had to know that I wanted to use a tree data structure where the nodes of the tree, where the root and the subnodes and the parent nodes, each of those was one of the mathematical arithmetic operations, and then the leaf nodes contained the actual function, or the actual value that's being operated on, such as a sine, a cosine, the pi function, stuff like that. So the way I actually write code with using a large language model is I actually write most of the framework, including to-dos, comments, and a basic structure of how it works. When I write code, I write like the basic version of how I want it to work first. And then what I'll use an LLM for is to refactor it. So I implemented, I was like, I want to use tree data structure, and then I'm going to use a stack to manage, nested functions. And I, wrote the initial implementation of that, and then I used, a large language model, basically said, hey, let's refactor this into a much, more easier reproducible code. And doing it this way also gives you access to using it for an exercise in, identifying the edge cases. I think writing test cases is going to become much more important when it comes to writing good code, as the LLMs are going to be like, okay, what test cases do I have to pass? I still think there's obviously still the concern that it might just write code or hard code, a pass for the test. But I think test cases are going to become much more important, and being able to write those test cases. But as you can see through this code, there's some errors here still. Cannot attribute, left of class object. For the most part, it's working. This seems to be more like just an error with my linter for Python. But it came out with the original type, and then I just I wrote the basic structure for this. I wrote the framework and the bones. and then I use an LLM to help me kind of fill in the gaps, do basic debugging and parsing. And I genuinely believe that's the future of how these LLMs are going to be used in computer science and programming. The skill level is rapidly going to shift to theory and understanding the theory and writing and how to implement it. So I genuinely believe that computer science is very much going to be shifting to a much more theoretical form of the field, um, as well as a much more math focused form of the field. There's going to be less of an emphasis on programming because the hyper the hyper pressure of, you have to be able to implement a tree data structure in Java. Let's all be honest with ourselves. We don't learn anything from those kinds of exercises. You kind of learn, oh, this is how I want to implement. I know the basic idea of how this code works now, which is what I think the objective should be for these classes. But you don't really understand language. You can't just take a class in Java and be like, I know Java. And I know that people are going to be like, well, no one ever claimed that was the point. I understand that's not the point. But, 20 years ago, the most popular programming language in the world would have been, I think it would have been C++ or Java. Nowadays, Rust is becoming rapidly one of the most popular languages in the world. 40 years ago, when my dad was in university, they were doing everything in, I almost said Kotlin, they were doing everything in COBOL, and Fortran. So this idea that, this overemphasis on programming languages and being able to write it in a programming language, I think is backwards thinking now. It's punishing students. It's going to punish students in the future who can't adapt quickly. So I think that, computational mathematics or even just a pure mathematics field with computer science classes on the side related to CS theory is going to become the ideal path for programming, because we're entering an era of programming and software engineering specifically. I'm going to differentiate between that and, theoretical computer science. We're entering an era of programming and software engineering where instead of the limit being your ability to write code, the limit is going to be A, your creativity, B, your ability to think outside the box, and C, your ability to read code, understand what it's doing, and understand, where there could be potential bugs. You know, everyone is having a junior developer in their pocket now. There's no denying that. We have services like Open Router, ChatGPT, and all these services. It's, everyone has access to this technology now, and I think where it's going to where people are going to be able to start differentiating themselves is if they're able to use it to improve their, to quote, improve their productivity. And I'm putting that in quotes only because this entire myth of the 10x engineer, in my opinion, is bullshit. It's more a matter of, can you incorporate the skill set and learn how to work with it? Think of large language models as more of a complexity of, a much more smarter autocomplete. It'll still benefit a lot from having a framework, but I think we're approaching an era of programming where creativity and the ability to think outside the box and the ability to understand computer science concepts and be like, here's our problem, this is an idea of how we can implement it, and here's how to do the basic framework, and then you work with something like a large language model to help implement that. Because I think that's where large language models really thrive, is the ability to write code. But this idea that it's going to replace software engineers is ridiculous. So there's still going to need to be software engineers. I think we're going to start seeing the term software architect thrown around a lot more, though, because there's going to be less of an emphasis on writing the code and being able to be like, this is what we need. But that's kind of my take on the state of computer science, programming, software engineering in 2026. We'll probably come back in 3 years and this video is going to have aged horribly, or maybe I was bang on the money for all I know. But I'll continue making videos talking about my different projects and creativity. But needless to say, I don't think we in the computer science field should necessarily be worried about AI taking our jobs. I think we should be focusing more on how can we use AI/large language models to completely uncork our creativity and our ability to think outside the box. Because how well you can write a function is no longer the limit. How well can you debug? How can you refactor? How can you read and identify code and think outside the box is what's going to get rewarded in the future. You know, the age of programming is, in my opinion, coming to an end, and the age of software architect is beginning. But that's all I have to say on the subject for right now. So talk to you guys later.